Okay, so again, welcome to today's central exercise class. Today we'll be discussing sheet number 4. As usual, we will be available for questions on live chat. So if you haven't done so, please open chat.tum.de and join this channel here, MA9714CE. We'll take questions there. And today Arda is the moderator of the chat channel. He'll take your questions and he'll forward them to me so that we can answer them live here on the stream. So Arda, would you please switch on your video and introduce yourself?
Hello everyone, I'm Arda. I'm one of the tutors on Thursdays and I will be your moderator for this webinar today.
Okay, thanks a lot. Good. As usual, I'd like to start with a quick question first to see which types of questions you found challenging on sheet number 4. So I'll start the poll right now. Let me take a minute to answer that. Which of these did you find most challenging? Okay, so that's pretty much what I expected, to be honest. Determination of tangential planes is something that seems hard right now. Maybe we'll do one more example for that if we have time in that central exercise session here. Otherwise, we'll just put something on one of the next sheets. Okay, computing gradients or Hessians, that should not be too hard for you, and that seems consistent with what you think. Determination of directional derivatives, that's something that is actually going to turn out to be pretty easy once you watch this week's videos. So maybe we'll have time to discuss this as well in a minute. Okay, so let's close this for now and have a look at today's exercise sheet. So today we mainly have 2 problems on the sheet. The first one is about gradients and Hessians, and maybe we can also do a directional derivative right there to see how that is done. And sketching functions. So let's start with this. That's problem C47. Here we have a function f that maps R2 to R. And it is defined by f of x1, x2 is x1 squared minus x2 squared. The problem asks you to sketch the level sets of f and the graphs of the restrictions of f to the coordinate axis, and also to determine the gradient and Hessian. So let's start with that. I'll start with the restrictions to the coordinate axis, because that will also give us a hint on how the graph actually looks. Okay, so if you want to restrict the graph to the x1 axis, then basically what we do is we consider the function f1 of lambda, that's just defined as f evaluated along the x1 axis. And the x1 axis, well, it's basically just the origin plus a line in the direction of 1, 0. So lambda is the parameter that takes us along this line. So what we do basically is we just vary the first variable, the 6,1. That's lambda now, and the second stays put. In this case, it's 0. Okay, and what happens is, oops, we just get x1 squared minus x2 squared. x2 squared is 0, so that term just vanishes, and x1 squared becomes lambda squared. Okay, so that's the restriction to the x1 axis. And just as a side note, if I were to restrict that on a parallel line to the x1 axis, so I could also do something like some fixed point x1 star, x2 star, and then adding lambda 1, 0. And I'm moving along the x1 axis anyway, so it doesn't really matter which x1 I'm using. So I could as well start at 0 here. I'm moving along that whole line anyway, so it doesn't make a difference. But it makes computation a little easier, of course. Okay, so basically that is the same thing as f of lambda and a fixed x2 star. And this is simply lambda squared minus x2 star squared. So what you have here is this f1 restriction basically means the graph is a parabola shaped like this. And if you're moving that in x2 directions, that line, so you're looking at parallels of the x1 line, then you get basically the same parabola, but shifted by that constant x2 squared, x2 star squared. Okay, so basically the graph looks a little like this. Let's have a quick look at that. So the graph of that function f1 basically is this parabola here. Okay, so that's f1, and this here is the x1 axis. Okay, for f2 we can do the same. So f2 of lambda, well, that's basically f evaluated now along the line origin plus lambda 0, 1. So we get f of 0 and lambda, and this is 0 squared minus lambda squared. So almost the same, but we have a minus in front of the term now. And again, if we were to look at parallels of that line, some x1 constant, again, x2, the constant can be set to 0 because we're moving along the whole line again, like this. That means we have x1 star and lambda, and we get x1 star squared minus lambda squared. And remember, x1 star is a constant, so again, we have the same parabola, just shifted by that constant x1 squared. Yeah, so if you're moving along the axis or parallels of the axis, then we always get a graph that looks like a parabola. Okay, we can also quickly sketch that one here. So that f2, very similar. Let's draw this in orange. So basically that one looks like this. Okay, so that's f2 of lambda. Okay, so what you can see in particular is whether you're moving along the x1 axis or along the x2 axis makes a difference in how that parabola looks like. In one case, it's open like this, and the other case, it's open like this. Okay, so if you're moving away from the origin, the graphs will look like parabolas, but in one case, they will open on top, and in one case, they will open on the bottom. And you can, of course, use that to determine the surface plot if you want to, or also the level sets. So let's just have a quick look at how these look. I'll give you another screen so that you can look at an actual plot here. Okay, you should now be able to see my plot. Okay, so this here, this surface that you can hopefully see now, that is how the graph looks like. And you can see here's the x1 axis in this direction here. That is the x2 axis. So if you're moving along x1 axis, you can see the graph locally looks like parabolas like this, yeah? They open on the top. And if you're moving along the x2 axis, let me just see if I can turn this a little, can I? No. Well, maybe it doesn't work with screen sharing, but you can, I guess you can still see that, right? So if you are moving along x2 axis, then you have parabolas that look like this. So they open on the bottom. Okay. And you've seen functions like this multiple times now. Especially what that means is this point here at the origin. This will have a gradient of 0, but of course it's neither a local maximum nor a local minimum. And we're going to investigate that a little closer next week. Okay, and the contour lines of that graph, they simply look like this. Imagine you cut through that surface here, cut through that surface with a plane that is parallel to the x1, x2 plane. So that has all the same x3 values. Yeah, then you get figures that look like this here. Yeah, these are basically, again, parabolas. Okay, I'll include the plots in the final transcript so that you can later download those on Moodle as well. Good, so let's give you back the iPad screen. Okay, so we have the level sets. We have the graph of the restrictions to the coordinate axis. Only thing left is to determine the gradient and the Hessian. So let's do that. For the gradient, basically what we need to do is we need to determine the partial derivatives in x1 and x2 direction. So let's start with that one. So we start with df dx1 of x. That means we treat everything but x1 as a constant, and then just differentiate the function with respect to x1. Remember, the function looks like this. So we have x1 squared minus x2 squared. Oh, sorry. Of course, I should remove the f now, like this. So I'm treating x2 as a constant, and differentiating a constant means the constant will just vanish here. And I'll differentiate with respect to x1 only, so the result is 2x1. And same thing, of course, I can do for x2. So taking the derivative with respect to x2. This time I'll treat x1 as a constant, and I'll differentiate with respect to x2 only. And what I get is minus 2x2. Okay, and that means the gradient here of f, that's simply the vector composed of these partial derivatives. So we get 2x1 minus 2x2, that's my gradient. Okay. Next up is the Hessian, so we want to compute that as well. And that means we just need the second partial derivatives as well. So let's compute d squared f dx1 squared. That means we're just taking this result here, that was the derivative with respect to x1, and we take the derivative with respect to x1 once more. What we get is 2. I'm sorry. Of x, that is 2. Same thing can be done with respect to x2. So this here is the partial derivative with respect to x2. And again, we just differentiate that once more, again, with respect to x2. You can see what we get is minus 2. Okay, and if we now take the mixed partial derivative, we need that one as well, d squared f dx1 dx2 of x. So that means we differentiate with respect to x2 first, the inner derivative, and then that again with respect to x1. For example, so we take this one here and then differentiate once more with respect to x1. Well, of course, there's no x1 in that expression, so differentiating with respect to x1 means that constant will vanish, so we get 0. Okay, that function is obviously continuously differentiable here, so that means the other mixed derivative is, is the same. I wanted to write it this way. Okay, so we have finally the Hessian of that function hf of x that is 2, 0, 0, minus 2. Okay, so that's gradient, that's Hessian. And as you would expect, just to point that out, the gradient at the point 0 in particular, that is 0, 0. So the derivative at 0, so to say, that's 0. So we have a stationary point. And we already saw that there is still no minimum or maximum at that point. And again, we'll talk about this a little more next week. Okay, I think that concludes 4.7. Now let's see what questions there are about 4.7 before we move on.
There weren't any specific questions about 4.7. There was a question asking to maybe explain the differences between the normal form and the parameter form of a tangential plane. And
I think we can get to that when we do the example on this topic. So maybe save that, and I'll hopefully explain it there anyway. If I don't, just remind me.
Okay.
Should have time for that, I guess. Anything else?
Well, there was one more question, but I answered that.
Okay.
Yeah.
Good. So let's move on to 4.8. See that we can get this one done, and then we'll do the example on tangential planes. Okay, C4.8. So here we have again a function f defined on R2, defined as f x1 x2 equals x1 squared x2 divided by x1 squared plus x2 squared. And of course, this is only defined if x is not the origin. And to define that function on R2, we need to add a definition for the origin. We just say the function is 0 there. Okay, and the whole point of this problem is basically to establish the fact that there are functions that are not differentiable at a certain point, although the partial derivatives may exist. And that usually boils down to showing that one of the partial derivatives is not continuous at the point in question. If you've watched this week's videos already, you will know that there is a connection between the partial derivatives and the total differential that says basically if a function is differentiable, then the total differential is basically the gradient of the function. To be precise, it's the transpose of the gradient. Yeah, so we treat the gradient as a row vector instead of the column vector. That's the differential. But the existence of the gradient alone does not tell us that the function is actually differentiable. So it might still be the case that a gradient exists and looks nicely, but the function still is not differentiable. This reverse direction here, that is only true if all partial derivatives are continuous at the point in question. And that's what we are looking at in part C. So the function here is one that is not differentiable, although the partial derivatives exist. But it turns out that one of those partial derivatives is not continuous at 0 at the origin. And that means the existence of the partial derivatives is not sufficient for the existence of a total differential. It is sufficient if the partial derivatives are continuous. Again, that's continuing this week's video. So if you haven't watched those yet, just accept this as a fact for now, okay? So let's start with that problem here. Oops, sorry, part A. Consider f along lines through the origin and show that f is differentiable at the origin. So that if f is differentiable at the origin, then the differential can only be the vector 0, 0. That's what we're going to do now. So we're looking at lines through the origin. Lines through the origin. And those lines basically have the form LV is lambda times V1, V2, lambda in R for some arbitrary V. That's a vector in R2. That is not the zero vector. The zero vector is not a very suitable direction. So anything else is a direction. And that means this set LV for varying V that covers all possible lines through the origin. And we want to know how F behaves along such a line. So F restricted to such a line LV becomes, let's see. So basically the coordinates here are just lambda V1, lambda V2. So we have F of lambda V1, lambda V2. And we can just put that into the definition. For x not equal to 0, so lambda not equal to 0, that means we get lambda V1 squared lambda V2 divided by lambda V1 squared, plus lambda V2 squared. That's true as long as lambda is not 0, and we have 0 for lambda equal to 0. Okay, so from now on, to keep the notation a little more concise, I'll just follow this non-zero case. The other one is trivial anyway. So what happens in the non-zero case? Well, we have in the numerator, we have lambda squared times lambda. So that's lambda to the third. Then we have V1 squared, V2. Oh, there's a V2 missing, by the way. Let's correct that. That's not missing, but it's not readable. So like this. And then the denominator, we have lambda squared in both of these summands here. So we can take this out of the sum. That's lambda squared. And then it's V1 squared plus V2 squared. Okay, that means what we get here, well, the lambdas or lambda squared cancels out. So we're left with the one lambda from the numerator. And then we have just V1 squared V2 over V1 squared plus V2 squared. And you can see what that is. Well, basically, that last expression here, this term here, that's just F again, evaluated at V1, V2. So that's all in all the same thing as lambda times F of V1, V2. And of course, it's also true for lambda equal to 0, yeah? So that holds in general. That means if we restrict F to a line, basically the value is determined by F of the direction, and then just scaled by lambda, depending on how far we move along that line. Okay, what does that mean for the directional derivative? Let's compute that. Well, that means if we want the directional derivative in direction v of f at the point 0, that's the point that we're interested in. Maybe I should write this here, at x star equals 0. So x star equals 0 means we have to consider the point lambda equals 0 for all lines, because that's where they pass the origin. That means we're taking the limit as lambda tends to 0 of the function itself evaluated at a point that is not necessarily equal to 0. So what we have then is lambda v1, lambda v2, some point on the line specified by the parameter lambda, minus the function value at 0 at the point in question, so that's f of 0, and we'll divide that by lambda. That's just a definition of the one-dimensional derivative. So we're taking the derivative of the function f along that line with respect to the parameter lambda now. Okay, and well, you know, this limit here, so f of lambda v1, lambda v2, that's simply the same thing as lambda times f of v1, v2, just computed that. F at 0 is 0 by definition. And the denominator stays the same. Well, so what happens here is the lambda cancels out, and we just get f of v1, v2. And of course, that is perfectly defined for every possible choice of v1, v2. So no matter what the direction is, the directional derivative does always exist. Okay, so dv of f at 0 always exists with the value dv of f at 0 is f of v1, v2. In particular, we could compute the derivatives with respect to the axis. So the partial derivatives, dx1 of f at the point 0, that is then simply f of 1, 0. And if you just take a look at the definition of f, up here somewhere, here we are. So if you substitute 1 for x1 and 0 for x2, then this becomes 0 divided by 1. So that's just 0. Okay, and also d by dx2 of f of 0, that's f of 0, 1. Basically the same thing happens. That's 0 squared times 1 over 1. So again, we get 0. Okay, so that means the gradient of f at 0 is 0. And you know the gradient has to be in line with the total differential if it exists. So what we know from this is if the function is differential at 0, then the only candidate for the differential is 0, 0. Okay, so let's make a note of that. That means if f is differentiable at 0, then f prime at 0 could only be 0, 0, which is just the gradient of f at 0 transposed. Okay, so that's our candidate gradient or candidate differential. And now part B of the question is show that f is not differentiable actually, so that this candidate doesn't lead to anything useful. Before we get to that, let's see if there are any questions already. Arda?
There is one question that I'm answering right now.
Okay.
Other than that, no.
Nothing. Okay, good. So let's go on with B. Okay, B says show that f is actually not differentiable at the point 0. We've already established that if it is differentiable, the only possible differential is 0, 0. So let's just see how far that takes us. Okay, so if f is differentiable at the point 0, 0, then, well, by definition of the total differential, the following holds. Well, f at some point x can then be approximated. So we have this linear approximation f of 0 plus the differential at 0 f prime at 0 times x minus 0 plus the rest, the remainder, again at x minus 0 with, and the main condition on that one is that the remainder is small compared to the distance of x from 0. And what that exactly means is the limit of that remainder here divided by the norm of x that goes to 0 as x tends to 0. So that's the condition from the definition of total differentiability. Okay, and in this case, so here, if we have f prime at 0 equals 0, 0, then that means the second term here, that will basically vanish completely. This term here, f0, that's 0 anyway, by definition of the function. So what we have is the remainder is equal to f of x. And then we can just have a look at this limit and see if things work out. So f prime of 0 is 0, 0, and f of 0 is also 0. So that means f of x equals 0 plus that remainder. And I just write r of x, yeah? X minus 0 is obviously x again. Okay, so we can just use that to verify that condition. So we're now verifying the condition limit r of x divided by the norm of x goes to 0. Or in this case, we're going to falsify that actually. Okay, and to do that, of course, that limit needs to hold no matter how we approach that 0, whether we approach it on a line or on a spiral or some irregular way, that should not matter. And of course, there may be ways where the limit works out. But if there are ways where it doesn't work out, then the limit can't exist. Okay, and what we're doing is we're finding a possible way to approach the origin where that limit doesn't work out. And it turns out we just have to use a line along direction 1, 1. Okay, so consider R or F along the line, let's just say in direction V equals 1, 1. Okay, what happens then? Approaching the 0 means, so we have R evaluated at lambda and lambda, that's direction 1, 1, divided by x is now again lambda, lambda. And the origin corresponds to the lambda value of 0. So we're taking the limit as lambda tends to 0 of this expression here. Okay, we know already that R must be equal to the function f itself. So that's f of lambda, lambda. Now this norm of lambda and lambda, that's just the square root of lambda squared plus lambda squared, can be computed. Now we can also compute f of lambda, lambda. So let's do that. If you remember, this f is defined as x1 squared times x2 over x1 squared plus x2 squared. So x1 and x2 both are lambda now. We've seen something like this before. So what we get here is lambda squared times lambda over lambda squared plus lambda squared. And we still have this square root here, this one. So that's the square root of 2 lambda squared. Okay, so that comes to limit as lambda tends to 0. So what do we get here? We have lambda to the third here. And in the denominator, we have 2 times lambda squared and square root of 2 times square root of lambda squared. So that's 2 times 2 times lambda squared times, and the square root of lambda squared is almost lambda, with the one exception. If lambda is negative, then the square root is still positive, so we need to take the absolute value here. Okay, so that's what happens. And of course, we can now cancel out a few of those lambdas, so we're left with lambda over 2 square root of 2 absolute value of lambda. Okay, so that's the expression here. Now let's evaluate that limit, and there's an absolute value in there, so the evaluation becomes easier if we make a case distinction and evaluate that by taking lambda from above and from below. So let's take lambda greater than 0 first. Then this expression here, this can be simplified because we know lambda is positive, so the absolute value does not really change anything. We can just leave it out, get this here. So the result, we can cancel out the lambda. The result is then 1 over 2 square root of 2. And of course, we have to do the same thing as lambda tends to 0 from below. So this time we know lambda is negative. And that means the absolute value of lambda is the same thing as minus lambda. Yeah? Minus a negative number is positive again. So again, the lambda cancels out, but the minus sign stays. So we get 1 over minus 2 square root of 2. And as you can see, the two limits do not agree. So that means the limit from below is different to the limit from above. And that means the limit itself does not exist. Okay, so that limit as lambda goes to 0 of lambda over 2 square root of, 2 square root of lambda times absolute value of lambda does not exist. And that in turn means we got that by computing the limit of r of x over the norm of x as x approaches 0. That does not exist either. And that in particular means it does not tend to 0. So that remainder does not behave nicely, and that means the function is not differentiable at 0. Okay, so that's what happens in part B. And before we start taking questions about this, let's again have a quick look at how this function looks like. Let me get you the other screen share again. So that's the old one. Here's a plot of that function here. And you should be able to see this, looks a little strange here. So here's the origin at 0. Basically, there's a line coming from the top here, moving through the origin, straight through the origin, moving down there. That meets with a line from that direction that does the same. Here's a line that basically goes almost straight through. It seems like that in that plot here. So at 0, some strange things seem to happen, which you can't really see in that plot because the resolution is limited, of course. And that function does behave nicely outside of 0. It's just where all these lines here meet that it doesn't quite work out. So that's how that function here looks like. And just to make this complete, this is how the contour lines look like if you want to look at that from that perspective. You can also see here, function comes from positive values, passes through the origin, goes to negative values, and here's that other line coming from that corner, passing through 0, going down to negative values here. That corresponds to these two lines here, basically. Okay, so that means whatever tangent you're trying to place at this origin will never be able to work out because there's different slopes from different directions meeting there, and they will not be able to kind of agree on a common slope for the tangent. That's why the function is not differentiable. Okay, let's see if there are any questions before we discuss the last part.
One question was, how do we know how to use the 1, 1 vector for the r along the line?
Yeah, good point.
1, 1 vector.
Yeah, we don't. Yeah, so the main thing about this is that's taking a good guess, basically.
Okay.
Basically, you have to find a direction where this doesn't work out. And of course, the simplest thing you can do is you can look at directions and lines, yeah? And that's what I did. I looked at all lines with varying directions. So basically, I computed this limit for general V1, V2, and then I tried to find a V1, V2 combination where it breaks. And the easiest one I could come up with is setting V1 and V2 equal, so to 1, 1. Yeah, so that's basically trying to poke around with that function and making it break, getting a good idea of how that happens. So in this case, obviously I told you what direction to look at, but if you don't know that, that's some work to figure that out. And just as a quick reminder, it need not be a line. So it could also be that that function behaves nicely along all lines, but maybe there's a spiral going into zero, a death spiral that shows the function is not continuous or something like that, yeah? It need not break along a line. It's just a nice coincidence that it does.
Okay, so next question is whether it wouldn't be enough to say that one of the partial derivatives is not continuous at x is equal to 0, and would that not be enough to say that the function is not differentiable at x is equal to 0?
Yeah, that would be sufficient. So if the function is differentiable, then all the partial derivatives exist and are continuous. And in C, we'll show that there is a partial derivative that is not continuous. That's exactly what happens here. Yeah, so that would be sufficient, of course. So if you did C first, then of course you could just answer B by referring to C.
And one more question we have, what happens in the step where the norm is simplified with next term?
So let's see, which step are we referring to exactly?
The step after we plugged in lambda in the expression.
So after this one here?
Yeah, well.
So that's a definition of the norm that happens here. Then this happens here. So that's the next step. This is when the norm is simplified. This here actually belongs to F, yeah? It doesn't have to do anything with the norm. That's the norm here. Well, just say this lambda squared plus lambda squared is 2 lambda squared. So nothing interesting yet. And then I'm breaking this up. So I'd say, well, square root of 2 lambda squared is the same as square root of 2 times square root of lambda squared. And the square root of lambda squared, well, that's just lambda. With the one problem that if lambda is negative, then of course the square root is not negative. So for negative lambda, the absolute value has to be taken here. And for positive, it doesn't really matter. So we have to use that expression. And that is precisely these two terms here. The other two, these two here, those come from this expression here. I hope that explains it.
And continuing that, actually, there's also one more question. Why does the lambda shorten in last step? So basically, how do we cancel the lambdas out?
How do we cancel the lambdas out? So what happens here, let's see, is we have this lambda to the third here and lambda squared here. So what I'm doing is I'm basically writing this as lambda times lambda squared, and then I cancel lambda squared. Yeah, so 1 lambda remains here in the numerator, and no lambda remains here in the denominator. I don't cancel the lambda with the absolute value of lambda. Yeah.
Yeah, I think they were asking because we changed the limit from to 0 to it goes to 0 from above 0, and that would let us get rid of the absolute value.
Yeah.
And then
You mean in this step here and the
yes,
next one? Okay. Yeah.
was actually
Yeah.
asking that.
Right. So I cannot cancel this absolute value and this lambda yet. So what I'm doing is I'm splitting up the limit in two cases. I'm computing this one first. Lambda goes to 0 from above, and then this one, lambda goes to 0 from below. And if both agree, then I have my limit value, and then I know the limit exists. And if I have this condition here, I know that lambda is positive, so I can just leave off the absolute value, get here. And then, of course, I can cancel the lambda. And same thing happens here. In that case, I know that lambda is negative. So that means the absolute value of lambda is the same as minus lambda. And again, I can now cancel those lambdas here. Yeah, I'm left with a minus sign, this one here. But the lambda cancels out and just a constant remains. So I don't have to compute the limit anymore. Yeah, limit is constant.
Okay. So one funny question about whether it would be enough to say that the function is not differentiable at x is equal to 0 if one of the partial derivatives is not continuous.
Yes, so if one of the partial derivatives is not continuous at 0, then the function cannot be differentiable at 0.
Yeah, that question then was turned into, so why did we go through all this trouble?
Because we didn't know yet. I mean, we could also do C. Yeah, as I said, you could also just do C and then argue one of the partial derivatives is not differentiable. But as of yet, we don't know whether the partial derivatives are differentiable or not. Yeah, I mean, of course, the result of this part also tells us there must be something wrong with the partial derivatives. They cannot be all continuous. And of course, if we know that beforehand, then we didn't have to go through all this trouble, but we just don't know.
Okay, they understood that.
Good.
Let me just see. I'm having a hard time understanding the question. So why does the delta V of F0 always exist with delta V F0 is equal to F of V1, V2 is the question.
I need to write this down. Didn't get that in the first attempt. So why does dv like this? I'm guessing he means the directional derivative of f at 0?
Yes, exactly.
Why is that equal to what expression?
dv f of 0. Oh, sorry, always exists with dv f of 0 is equal to f of v1, v2.
Okay, so why is that true? Well, because we just computed that. Let me switch back to part, why did we do that? Part A, actually. So here what we proved first in part A is that f of lambda v1, lambda v2 is equal to lambda times f of v1, v2. And then we just computed the partial directional derivative of f at 0, this expression here. We just used the definition of the one-dimensional derivative. We then used what we know here. Yeah, substituted that here. And then that lambda just cancels out and we're left with this one. So obviously that function value is defined everywhere, so that limit exists. And we know the value. Yeah, so that's easy, so to say. Okay, is that it?
I think just one more question. I'm hoping I'm not forgetting anything. The question is just, how did you come up with the directional derivative?
Just by definition. So I'm just using this definition here to compute the directional derivative. Yeah, so basically the directional derivative is the derivative of the function constraint to that line in direction v. That function looks like this. And now I'm just using the definition of one-dimensional derivatives. Yeah, that just says if you want to take the derivative at some point x star, what you do is you take the limit of f of x minus f of x star over x minus x star as x goes to x star. That's the definition of one-dimensional derivatives. If that exists, then this is f prime of x star. And in our case, x star is 0. So this is what we want to know. And the x, this x here is just a point along the line. So any point along the line can be expressed as lambda times the direction of the line. That's what we're doing here. Okay. So I hope that settles this question.
There are no more questions.
Good. So let's quickly have a look at C as well. So C then asks us basically to verify that actually there is something wrong with one of the partial derivatives, as you suspected already. One of those cannot be continuous at 0. And I'm even telling you which one to look at. That's the second partial derivative here. So first thing we need to do is, of course, we need to compute that. So part C. For x that is not equal to the origin, we can easily compute that by just taking that derivative here. So let's do that. So what we need to do is we need to compute df dx2 at that point x. You all know the expression of f. It's basically quotient rule applied. What you get if you do that is, I'm just giving you the result. You can do the differentiation yourself, I hope. It should look like this here. So x1 to the 4th minus x1 squared x2 squared divided by x1 squared plus x2 squared squared. Okay, so that's how that second partial derivative looks like outside of 0. We've already computed the gradient at 0. So we know from A that df dx2 at 0 is 0. And that means the question is, what about the limit of this df by dx2? Is that also 0? So the question is limit of df dx2 x as x tends to 0, is that also 0? And again, you have to consider all possible directions for getting it 0, not just directions, all possible paths that somehow end up at 0 to actually compute that limit. Or if you want all possible sequences that tend to 0. It's not sufficient to check this along a line, and even less to check this just along one of the axes. Let's just guesses that you could take. If it breaks along one of the axes, of course, then we're done. But maybe it doesn't break along the axis. Maybe it breaks along some different path only. So again, we have to take a guess, or we have to do some computations to find out where the problems are. And I did that for you again. So I'm telling you the line that we could look at here, for example, is the x1 axis. Okay, so we look at that function along the x1 axis. And that means what I do is I'm again taking a limit of lambda to 0 of df dx2 along the x1 axis. So I'm moving my line in that first direction only, and the second direction stays at 0. So I'm computing this limit here. Okay, and doing that, let's just substitute the expression that we computed above here. So if x1 is lambda, then this term here remains. x2 is 0, so this term vanishes and this term vanishes. So we get lambda to the 4th over lambda squared squared. Oops, sorry. So that's lambda to the 4th over lambda squared squared. And you can see this evaluates to 1. So that means the limit is 1 if we're moving along that line, but we already know the partial derivative should be 0. So obviously it's not continuous. Okay, so as df dx2 at 0, 0 is 0, which is not equal to this limit here, which is 1. That means df dx2 is not continuous at the origin 0, 0. Okay, and again, I gave you that direction. It's not that easy to actually find that direction by yourselves. Yeah, so if that were an exam problem, I will probably provide the direction to look at for you. Okay, any questions on this problem here?
A couple questions are coming up.
Mm-hmm.
There is one question saying, can't we just plug in x1 is equal to 0 and x2 is equal to 0 to see that the partial derivative is not defined?
No, we cannot just plug that in. I mean, we're taking a limit here for good reasons. And the reason is the limit is not defined with this term. It is very well defined at 0. We computed that in part A. So the function, the partial derivative is defined at 0 and it has a value of 0. The problem is not that it's not defined. The problem is that it jumps at that point.
And the student is typing.
Mm-hmm.
So the question is whether you could show them how we would approach 0, 0 not in a linear way.
How would approach this not in a linear way? Well, I don't know if the limit works out, obviously, but I can show you the principle of doing that. So if you would not move along a line, but some other path, then of course we need some description of that path that we could work on. So for example, let's say we have different path. Let's call that P for path. We have a function that again depends on one parameter and that describes that movement along the path as we do for the line. Yeah, the line is also a path, just a very restricted one. So for example, we could have a path that spirals into the origin. Yeah, let's try to do something like that. That would mean spiral. So we have some amount of moving along a circle. So this here, this vector cosine of lambda sine of lambda, that would describe a circle going round and round and round. And now we need to reduce the radius of that circle as we, let's say, as we increase lambda. And we could do something like 1 over lambda, for example. Yeah, that means as lambda gets bigger, the radius of that circle decreases, so we spiral closer and closer to the origin. Yeah, so that looks, the path looks something like this. Okay, but of course there are numerous ways to do that, and this might not be the path that you want. So that's a very hard thing to guess if you don't know the path. For example, you could, instead of dividing by lambda, you could divide by e to the square root of lambda, or by lambda to the 5th, or something like that. And you could also move the cosine faster than the sine, or whatever you want to distort this a little, or just move faster, or reduce the radius faster. There's multiple ways to do that. And we'll talk about curves like this. So this is called a curve. We'll talk about these later on when we treat integration along curves a little more. But that's how you would describe a path like that. And again, you'd have to know what path you want.
Now, one question, which is not that hard. So is a function continuous at a point when the limit for x going to that point is the same as the function value at the point?
That's precisely the definition of continuity, right? Yeah, so the definition of continuity is a function is continuous at a point if and only if the limit as x approaches that point x star is the same as the function value. So if that holds, then and only then f is continuous at x star.
And the next question of the same student is, could you show what it would look like if we chose v is equal to 0, 1?
V is equal to 0, 1 like this?
Yes.
Well, you just could substitute it in there. I don't really know what happens. So it probably doesn't make much sense to compute that now. But of course you could just take the expression that we have. Again, I'm guessing we talk about that second derivative here still. This one here. And you could just substitute direction 0, 1. So we're moving along that second coordinate only. So x1 becomes 0, x2 becomes lambda. And that means with the expression that we have, that would just become 0 to the 4th minus 0 squared times lambda squared divided by lambda 1, of course. Come on. Divided by, that's 0 squared plus lambda squared squared. So what you will get here is 0 over lambda to the 4th. Of course, that's just 0. Okay, so you could use that, but in that case, things work out nicely. So along that line, the second partial derivative is just 0 everywhere, and that's not a contradiction to it being 0 at 0.
Yeah, that was. Okay. That were all the questions.
That were our questions. Okay, good. It's 4 o'clock already, but if you don't mind, I'd still take a quick look at that tangent example. Is that okay? Good. So let me show you that one. I've brought another example for computing a tangent here. I hope you can all see that one. So there's a function defined on R2 to R, defined like this. Looks a little complicated, but that doesn't really matter. And we want the tangential plane to that graph at a point. The point is now 1 minus 1, so it's not 0 this time. Again, makes it a little more interesting. In that specific form here. And of course, you'll recognize that that is the normal form of the tangent. And that's actually, as you might have guessed, a problem from one of the last exams, actually from 2017, I think that was. Okay, so the objective is to determine that tangential plane. How do we do that? Well, let's try to do that. As you know, basically, the tangential plane is more or less the differential of a function, more or less, because what it is by definition, what the differential does is approximate the function linearly. So that approximation works like this. F at some point x is equal to the function value at a point x star that we want the approximation at, plus the differential at the point x star times x minus x star, and then plus this remainder at x minus x star. So that first part here, without the remainder, that is the linear approximation of f. at x star. And what that means geometrically, a linear approximation of a graph, that's just a tangent plane at the graph. So that's the plane that we want. That's the tangential plane of f at x star. So we basically need to compute this expression. And that means what we want is we need the function value. That shouldn't be hard. We need the derivative or the differential. That might be a little harder. And of course, we need to mix it with this expression here. So basically, we just leave out the remainder, and then we have the tangential plane only. Okay, so let's just do that. So what we need to do is we need to compute the gradient to see if the function is actually differentiable, and if so, what the value might be. So let's differentiate with respect to x1 first. So we treat x2 as a constant. That means what we get is, first term is e to the x1 squared x2 times 2x1. x2, sorry, forgot that. Plus, and we have that cosine term here. So the derivative of the cosine is minus the sine. So we have minus sine of pi x1, x2. And again, we need to apply chain rule here. And that gives us a factor of pi x2. So that's the partial differential with respect to x1. And for x2, things look similar. So then we have x1 squared x2 times x1 squared. And here we again have the cosine, meaning we again get minus sine of pi x1, x2. And this time we differentiate the inner function with respect to x2. So we get pi x1 as a factor here. Okay, so that's our gradient. We are specifically interested in the gradient just at the point that we want to approximate at. And this point is 1 minus 1 in this case. So if we enter that, what we get is, let's see, e to the minus 1 times 2 times 1 times minus 1, so minus 2, plus, plus, actually that's this minus and this minus 1 here, so that's a plus, pi times the sine of minus pi. And the second coordinate is e to the minus 1 again times 1 this time, minus pi sine of minus pi. Okay, if we evaluate that, the sine of minus pi is 0. So those second parts just vanish. And we are left with minus 2 e to the minus 1 and e to the minus 1. Okay, so that's our gradient. Obviously, the functions that we get here are continuous. So the function is differentiable, and that is actually the differential. So that means our differential at the point 1 minus 1 is actually e to the minus 1 minus 2 and 1, that vector here. And you remember we also need the function value. So the function evaluated at 1 and minus 1, we need to compute that as well. Let's see, the function was this here. So this is again e to the minus 1 plus the cosine of pi. So e to the minus 1 plus the cosine of pi. And the cosine of pi is minus 1, so we get e to the minus 1 minus 1. That's the function value. So that yields our linear approximation And that linear approximation is the tangential plane that we're looking for. So we call that T of X for a tangential plane. Yeah, so T of X is F at 1 minus 1 plus F prime at 1 minus 1 times X minus this point 1 minus 1. So what we're getting is, well, F is e to the minus 1 minus 1. Then this expression here, this differential was e to the minus 1 minus 2, 1 times x1 minus 1, x2 minus minus 1, that's plus 1. So what we have is, let's see, e to the minus 1 minus 1. Then we get minus 2 e to the minus 1 x1 minus 1. And plus e to the minus 1 x2 plus 1. Okay, so to get this in the desired form, of course, we need to do a little more simplifications. So that's e to the minus 1 minus 1 minus 2 e to the minus 1 x1 plus 2 e to the minus 1 plus e to the minus 1 x2 plus e to the minus 1. Okay, so that's our T of X, and that means that normal form of the tangential plane. What does that look like? Well, basically what we do is we replace the function value T of X with x3. Yeah, that's, I mean, in the graph, that function value is the third coordinate. So we just replace that. And we get x3 equals, let's collect all of this, minus 2 e to the minus 1 x1, that's the x1 part. Then we have plus e to the minus 1 x2, that's the x2 part. And then we have a few constants. Let's see. So we did that. We did that. We have e to the minus 1 plus 2e to the minus 1. That's 3e to the minus 1 plus another one. That's 4e to the minus 1. And then we have this minus 1 here. So just need to reformulate it in a way that the constant is on one side and the x parts are on the other side. So let's reformulate that by taking the x's to the left. Then we have 2e to the minus 1 x1 minus e to the minus 1 x2 plus x3 equals 4e to the minus 1 minus 1. So that's the normal form of the tangential plane. Okay, any questions so far? Before I show you how to get the parameter form?
Dr. Itter, so one question was that cosines of pi is -1, not plus. So could you go up?
Yeah. So here, cosine of pi is -1.
Yeah.
That should be correct, right?
Yeah, it is correct.
Maybe somewhere else. Did I get the wrong place?
Maybe. They are writing right now. Oh, they're saying it should be cosinus of minus pi.
Where are we? Of -1, so you need to get back at the, yeah, of course you're right, it should be cosine of -1. That's correct. It doesn't change the result though, right? Cosine of minus pi is also -1.
Okay.
Yeah, but thanks. Anything else?
No.
Good, so that's the normal form. And if you want the parameter form, maybe you can get that as well. So what that normal form basically is, it tells you, yeah, basically two things. There's this normal vector in there, that normal vector is a vector that is perpendicular to the plane. Yeah.
Sorry, Dr. Ritter. And one more question. They're saying at the end, plus 2e minus 1x1 is written, but
Plus 2e to the minus 1. Yeah. Yeah, you're right. You mean this one here, right? That should be a plus.
oh,
Correct?
yeah.
Yeah. Thanks a lot. Yeah, right. Right, that would have messed up my results. Good. Okay, let's get to the parameter form then. So how do I get the parameter form from this? Well, basically, what I was just trying to say is that normal form that contains a so-called normal vector, that's a vector that is perpendicular to the plane. And the normal vector just consists of the coefficients in front of the axis. So if we have this expression, yeah, sorry, on the next page here. This expression here, we could also write this in vector form by saying, well, that's the same thing as 2e to the minus 1 minus e to the minus 1 and 1 transposed x1, x2, x3 is 4 to the e minus 1 minus 1. Okay, and this here, that is called the normal vector of the tangential plane. That's a vector that is perpendicular to the plane, or just write orthogonal maybe. Orthogonal to plane. So that means every vector that is orthogonal to this one is contained in the plane, right? So basically the plane consists of all vectors orthogonal to 2e to the minus 1 minus e to the minus 1 and 1. One thing you have to watch out for, plus a shift. Yeah, so it's not the vectors, let me say that differently. So it's all the vectors that fulfill this equation here. And what that equation basically says, it's, well, it's all vectors where this scalar product here is 0, so they are orthogonal, plus a shift to get to this coordinate. So for the orthogonality, you usually place the plane such that it contains the origin, and then you can use that definition of scalar product equals 0 means the vectors are orthogonal. Yeah, and then you shift it such that actually the outcome is not 0, but a constant that is away from 0. That just means you shift the plane such that it doesn't contain the origin anymore. Okay, if you need to brush up on that, have a look at what you did in Mathematics 1. That was a brief part on that as well. Okay, so if you just accept this for a minute, the plane consists of all vectors orthogonal to this plus a shift. That means if we want the parameter form, we just need to find two linearly independent vectors that are in the plane, and then compute the right shift, so a point that is also contained in the plane. So first thing we do is find two linearly independent vectors in the plane. And to do that, we need to find two vectors that are orthogonal to the normal vector. This is 2e to the minus 1 minus e to the minus 1 and 1. Okay. Anything we do just needs to be linearly independent. So the easiest thing is just to take a good guess. So here, for example, we could just say, well, let's set the first coordinate to 1 and the second to 0. Then we have a scalar product of this vector and that one so far. That is 2 e to the minus 1 plus 0. And then there's this last coordinate. So this here times 2 e to the minus 1 minus e to the minus 1 and 1. So far, this is 2 e to the minus 1 plus 0. So let's use that last coordinate to correct, to get back to the value 0 that we want. Yeah, we want them orthogonal, so the scalar product should be 0. And that means what we have to set here is, well, we need to get a value of minus 2 e to the minus 1 to get back to 0. And we have this 1 here. So 1 times what is minus 2 e to the minus 1? Well, precisely this value here. So we're using that to get a result of 0. That's a vector that is perpendicular to the normal vector. And let's try to find a second one. And again, we want to make sure that it is linearly independent of the first one. So to be sure, we just say, well, let's set this first value to 0 and the second to 1. And we can be sure that these two vectors are linearly independent. And again, let's see what the outcome is. Well, this time it's 0 minus e to the minus 1. And again, we need to correct to get a value of 0. And the right correction here is if we put an e to the minus 1 here, then we get plus e to the minus 1, and those cancel out. Okay, so we found these two vectors that describe the plane. Only thing left, part 2, is find a point in the plane. And again, any point in the plane will do. And in our case, we know one of the points in the plane already. Here, we just use the point where we approximated the function, because that point is contained in the plane, obviously. Just use the point x star 1 minus 1. And then, of course, we need to add the x3 coordinate. Well, that x3 coordinate is just the function value at 1 minus 1, right? And we computed that one already. So it's 1 minus 1, and the function value was e to the minus 1 minus 1. So we can just use that point. And again, if you don't like it, just compute something else. Just have a look at this equation here and find any combination of x1, 2, 3 that fulfills this equation, and you've got your point. Any point's good. Okay, and what we get from this one is, well, the parameter form of that tangential plane. That is then, we're starting with that point here, 1 minus 1 e to the minus 1 minus 1. And then the two directions that are inside of the plane, we have lambda times the first direction was 1, 0, and minus 2 e to the minus 1. And the second direction was 0, 1, e to the minus 1, right? Yeah. And we just move along these two directions. So lambda and mu are taken from R. Okay, so that's the parameter form. Okay, any questions?
Nothing here.
Okay, great. We lost all already. A little more on approximations is going to be the topic of next week, by the way, where we're going to extend Taylor approximation from the one-dimensional to the multivariate case. And of course, this tangential plane is just a simple form of Taylor approximation. That's Taylor approximation with a Taylor polynomial of degree 1. Yeah, of course, you can take this further and get approximations through parabolic surfaces and surfaces of higher order. So we're going to talk a little more about this and related questions in the coming week. So next week, not this week. Okay, if there's no more questions, Harda, nothing come up?
No.
No.
Oh, someone's right. Oh, they said thanks.
Okay, great. So if there's no more questions, we'll conclude the session for today. I'll upload the materials in a minute so that you can have a look at those once more. Thanks for attending, and I'll see you next week. Just a quick reminder, this Thursday is a public holiday, so no tutorials this Thursday. Yeah, I'll put it on the Moodle page as well, so you don't forget. Good, so I'll see you next week then. Bye.